This is the beginning of the chemical kinetics unit. There are quite a few objectives for this unit, and I wanted to write them all down. We'll hit all of these objectives throughout the course of the unit. Okay. There's 2 pages of objectives. But let's look at partly like why do we need to look at kinetics at all? If you look at the De Beers "A Diamond is Forever" ad campaign, the question rises, is it really? Is a diamond forever? Let's looking at or using things that we learned in the energetics unit. So let's take a look at Gibbs free energy and find out if the reaction of carbon in the form of diamond, if it decomposes into carbon and graphite, is that process spontaneous? We know from thermodynamics that the change in Gibbs is equal to the sum of the Gibbs free energy for the products minus the sum of the Gibbs free energy for the reactants. Hopefully you remember that if the Gibbs is negative, then the reaction is spontaneous. Okay, so plugging in values from literature, we find out that, whoa, the Gibbs free energy for that reaction is negative, so it does mean that this is spontaneous. So I guess when I wear my engagement ring with the diamond, I should take a quick look before it turns into graphite. Although I have had my engagement ring for a fair number of years and I don't notice any graphite. So while it's true that her diamond, or my diamond, is spontaneously turning into graphite, it's happening very slowly. Okay, it takes actually billions of years for the diamond to go into graphite. So while thermodynamics can tell us and does tell us whether or not a reaction or an event is spontaneous, it does not say anything about how fast that reaction goes. This is what kinetic does. It's going to help us describe the rate of the reaction, the change of concentration over time. Why do we care? Well, okay, this was before you were born, but in the late 1980s in Chernobyl, which is in the Ukraine, there was a meltdown of a nuclear reactor. They evacuated people within a certain radius of the plant, and they estimate that it is going to be about 20,000 years before it will be safely inhabitable, meaning that the radioactivity levels are going to fall enough so that people won't get cancer if they move back into the area. Okay, and kinetics lets scientists estimate how long that's going to take for the dangerous radiation to go down to safe levels. In industry, chemical processing plants, they want to make products as quick as they can, and they want conditions that are efficient and have the best economic yield. Kinetics tells us a lot about that. How quickly can we make something? Also helps us to learn how to slow down reactions, such as the destruction of the ozone layer and our milk spoiling. It also helps us understand reaction mechanisms. And this explains how reactions happen at a molecular level by suggesting a sequence of bond breaking and bond making in steps to go from the reactants to the products. For the rest of this screencast is looking at rates of reaction to define or describe the term rate of reaction, to describe suitable, oops, not that one because that's in black. Analyze data from rate experiments is also something we're going to look at. So let's look at reaction rates. So the rates of reactions can be determined by monitoring the change in concentration of either reactants or products as functions over time. So in this reaction here, what we're looking at is A going to B. All right, so A, the red is my reactants, the blue then is my products, and you can see hopefully that the amount of blue in the containers increases over time as I go left to right. All right, so if we were to graph this change over time, we would see that if I look at the red, I start off with the concentration and it decreases over time as those reactants are reacting and becoming products. The reactant decreases in concentration. You can see the product starts off at 0 because at the beginning of the reaction I don't have any product, and over time that is what is increasing. Okay, an important thing to note, whether you are looking at an increase in product or a decrease in reactant over time, the rate is always positive. Okay, so it's the rate at which the reactant is decreasing or the rate at which the product is increasing, but either way it is a positive value. Okay. I just wanted to show you looking at these curves and a slightly different reaction, A plus 2B producing C. Again, we get that C curve starting at 0 and increasing, like leveling off over time, and then A decreasing. If you notice, B has a much steeper slope or curve, and that is because for every 1 mole of A, 2 moles of B. So the concentration of B is actually decreasing faster, and it has the steeper curve. Okay. From math class, if we look at this curve, we can get the instantaneous rate, okay, by drawing a tangent to a point on that curve and calculating the slope of that tangent line. The slope at the start of the reaction is going to give us the initial rate of reaction, and we're going to find that that is the one that we typically look at. And the slope gets less as the reaction proceeds because the amount of reactants is decreasing. So the slope, change in concentration over the change in time. Okay, so if we look at reaction rates, we have butyl chloride as my reactant reacting with water to form butanol and hydrochloric acid. The concentration of this reactant was measured over time, and it was measured in moles, decimeter to the negative third, and nope, just concentration. So moles, decimeters to the negative third using IB units over time. Okay. Taking the change in concentration over this change in time gives us the average rate for that time period, and we can calculate average rates for each of those time periods by using the change in concentration of that reactant over the change in time for each of those intervals. Important. Okay, so you can take the average rate, note that the average rate decreases as the reaction goes on. And that's because as the reaction goes on, there are fewer collisions between those reactant molecules. Okay, the rates of the units of rate that we've already kind of discussed, a lot of times in the United States, of course, it would be molarity per second, which is the same thing as moles over liters second. But the units that we should focus on using for rate, moles, decimeters to the negative third, moles, decimeters third over seconds. Moles over decimeters cubed, I should say cubed, is the same as molarity. All right, it's just a unit that they use in Europe, but get used to seeing it. I will try very hard to use those units as we go through, but I'm used to molarity, so hang in there with me. All right, so let's plot the reaction over time for that butyl chloride reaction. Again, we can take a slope of a line that tangents to the curve at any point to find the instantaneous rate. Okay. And the best indicator of the rate of the reaction is going to be the instantaneous rate in the beginning of the reaction. That's what people, when you talk about rate of reaction, that's usually what they are referring to, unless they say average rate of reaction. Why do we measure instantaneous? Okay, if you look, here's the average reaction rate, but that doesn't really give us a clear picture about what's happening at any point in time. So we do want to look at the instantaneous rate. So how do we relate these to stoichiometry? Well, in this reaction, the ratio of butyl chloride to butanol is 1 to 1. So the rate of disappearance of that reactant, the rate of disappearance is equal to the rate of appearance of the alcohol. It's 1 to 1. What happens if the ratio is not 1 to 1? We can relate these things using the coefficient in the equation. If you notice, for hydrogen iodide decomposing into hydrogen and iodide, for every 2 moles of hydrogen iodide, I make 1 mole of hydrogen and 1 mole of iodine. If we look at the rates, negative the rate of disappearance of that reactant divided by 2 is going to be equal to the rate at which iodide forms. And it's really just relating the balanced chemical equation. I find it's easier to remember this so I don't mess it up by flipping something. We can look at a general equation. Okay, if we have the equation lowercase a, capital A, what this means is that the coefficient is the lowercase letters, okay, with the molecules or chemical compounds being the greater. So negative 1 over little a, change of a over time, is equal to negative 1 over little b, change of b over time, and so forth. And that just helps you relate stoichiometry back to the rates. And that ends our first screencast.